platform for if you're trying to do a lot of qubits?
I cannot comment.
Because I mean, it seems like, I mean, it's like pieces of plumbing, right? You have to, if you were to build more qubits, then you just have to add more pieces of plumbing.
Yeah,
They have very limited cryostat space.
They have their own agenda, so I cannot comment too much.
So I guess you chose the example because we had interaction.
Because I have been doing this simulation, so I don't want to do something from scratch.
The regular superconducting qubit. Okay,
Yeah.
that makes sense.
Okay. So now let's talk about the project, right? So after you learn this, the project is all about superconducting qubit readout, right? So you already done the lab 1 to lab 10 very fast, right? In part 1, very good. And so then based on that, let's talk about the energy participation ratio, right? So this was proposed by Dr. Minev. I think he was in Yale, but now he's in IBM. So it's a very for ours, what we have learned is a difficult theory. We cannot understand all of them for what we have learned so far, but it's good to just have an idea. So what you're trying to say is, you remember, in order to quantize the circuits, you need to go through Lagrangian, and then Hamiltonian, and then quantization, do a lot of stuff, right? Same for here, when the theory is developed, you need to go through all this. But then eventually it's broken down into that, what is the fraction of energy for the energy mode M stored in element J? So if you're given a circuit, however complicated it is, right? It's not applicable to everything, however, but most of the circuit. We just want to find out what is the energy stored in a particular element. Because from there, then you can predict many important quantities. And to find out how much energy is stored in different elements becomes a classical problem. You can just use HFSS to do the simulation. And that's what you are doing for part 1, right? The energy participation ratio is PMJ. It means for J, for example, let's say we're talking about this element, Josephson junction, we're saying that for mole 0, we have mole, right? Just now you were asking me, for example, this, right? Mole 0 is going to be this one. But also the transmon itself has a mole also, right? This one. So when you do the simulation, you actually don't know which mole it is. So you need to look at it carefully. Sometimes like last time, some of you keep increasing the mesh point, and then the 2 mole, then you see something like this. It can be TMO, yeah, those mode if it exists. Some of them does not exist, but yes, but different mode, like also different frequency, right? Yeah. So last time, some of you keep increasing the meshing, right? This is number of paths. And then you look at the eigen frequency, right? And one of you told me that, hey, it's suddenly like this, go up, and then this one go the other. That looks like repelling each other, right? But I think this is just because the resolution was not good at the beginning, and eventually it turned out your transmon actually has a larger mode, larger frequency than the other one. And you look at the plot, you thought that this mode is still the cavity mode. Okay? So the cavity itself has a resonance frequency. The transmon itself has a resonance frequency because it has an LC circuit. Okay? Now, anyway, so the good thing of this is that now you can use HFSS to do the eigenmode simulation, right? So what do I want to say here? A lot of equation, again, we don't need to really understand, but it's good to have some feeling to appreciate what we have learned. For example, the Hamiltonian of the full circuit, it is decomposed into the linear part and non-linear part. And the so-called linear part is this. This one, I hope, again, you feel very comfortable. What does it say for this part? Is energy equals to what? Yeah. And this is just the number of photon, right? N dagger N, right? That's the N, right? So you're just saying that the number of photon times the photon energy is the energy in the cavity, of course. And this is, again, number of Cooper pairs, right? Or the unit energy this is not really Cooper pairs. Sorry. This is not Cooper pair, right? This is, is it Cooper pair? I'm also confused. But the quantum energy, number of quantum energy, because this is the, when you map to the Bloch sphere, you get this normal precession energy, right? H bar Q, right? So that energy, number of quanta of that energy, right? So that is the linear. But then they have nonlinear term. That is due to the Josephson junction, right? Cosine EJ times cosine phi. Okay? And then it also is this phi j. And phi j turned out to be these two components. It's just the annihilation operator plus the creation operator and the annihilation operator plus creation operator. These two are the 0-point fluctuation. We have learned this before. If you remember, you recall the LC circuit, LC tank. At that time, we did introduce LC tank, right? We did introduce this one, if you recall. The flux equal to 0-point flux energy times A dagger plus A. So again, this is no surprise, right? Although we did not prove it, but at least we feel that if we try to prove it and if we were able to prove it, we would get a term like this. Okay, and this you can go to the paper. I actually did not went through the derivation. Now, then, what is the energy participation ratio here that we care about? Is the inductive energy stored in the junction divided by the total inductive energy in mole m. And sorry, I forgot to say this. And this can be computed by the electric and magnetic field. And that's why HFSS can do that. And this, we just take it for granted. The energy participation ratio equals to this term. Again, this is the FH value, the ratio between the linear term and this term, right? And then this is the 0-point fluctuation. Again, it depends on EJ, all this thing. And then this is the anharmonicity. Right? And this is the Cross-Kerr. The message here, all I want to say, again, do not think that you need to memorize this or put in cheat sheet. All I want to say is I just want to say that all this Cross-Kerr, whatever, how much it is shift, can be computed by the energy participation ratio. And energy participation ratio can be computed from the electric field and magnetic field. If you solve it self-consistently, then you can get that, right? And that's how it is, right? The Qiskit developed by Dr. Neff was like, it called the HFSS, set it up, done all the computation to find the Q, to find the Eigenmode, and then to find the energy distribution. Then its code is going to compute the energy participation ratio. From there, it can compute the Cross-Kerr and harmonicity, etc. Okay? Now, something that we overlook is that, how about the Josephson junction energy? HFSS cannot simulate superconductor. It cannot simulate Josephson junction. So what do we do? If you remember in the part 1, you were asked to draw a line and then assign a lump RLC boundary. What we did is just apply, for example, 12 nanohenry to here. It's just to tell HFSS, this region has 12 nanohenry. Take it as a boundary condition. And that is to mimic the Josephson junction inductor. There's actually some problem with HFSS. It actually, I don't know if they solved this bug already, right? I don't know if they fix it, but let's just assume it works. So at that time, we find some problem, and then I try to say, can I really maybe just make a real inductor with 12 nanohenry? Now look at this. It's so complicated, so big. Here I just want to show you, Josephson junction, The great thing about it is also it has a big inductance with a small area. If you want to get this inductance, you need to have so many layers of metal with such a big area. This is talking about if you only have 2 layers, it's talking about very large layout. And then of the quality factor is going to be very bad also, right? So this just for you to contrast, to appreciate. Yeah.
These are the tricks the physicists have in their book.
What tricks? Oh, you mean this one? Okay, yeah. But there is a problem here. But it's okay for this project. If you really do research in this in the future, you can talk to me. What are the possible problems? We post this question in HFSS, but I don't think they have solved this problem. Okay, so in this project, what I want you to do is very simple, right? Because this is a new class, I did not plan it well, and you only have 2 weeks. I just want you to learn as much as you can. You only study the mode 1 and mode 2. And make the accuracy to 1%. You don't need to go to too low. I will talk about accuracy, how you choose accuracy later for a real application. And also limit it to 10 passes, because I know some of you want to get perfect results. You will go to 10, 11 passes, then your laptop will crash. It's just a too much not match point. And also keep the LJ equal to 12 nanohenry. Don't change it, because that is going to change your result. So I would like you to change the sapphire location. We have 2 ports, right? And then we have a sapphire moving back and forth, or you can move it up and down. You can also change the JJ location within the sapphire. Now, when we created the project, if I remember correctly, I show you how to create with parameters. So that you only need to switch the parameters, right? You don't need to redraw everything. If you find that you need to redraw, you better go back to parameter. Otherwise, you cannot finish this project. Okay, so you only need to shift, let's say the center shift it, and then the width shift it, right? Then study how the cross-Kerr, Q, and resonance frequency changes, and explain your observation as much as possible. And now you should understand why cross-Kerr is important, because it helps us to distinguish. Somehow the one I sent you have very small cross-Kerr. I did not spend time to further to try it. So don't worry too much if you cannot make it good, but I want you to show me that you were able to change it either smaller or larger, and explain why. Okay? Q, again, you know it is important because just now you asked, because it's like this is also the cavity that you will do manipulation sometimes, right? So you want to have a high Q, okay? Resonant frequency, of course, if you turn out need to go to 20 gigahertz, it's not going to work. You want to maintain at 3 to 10 gigahertz, for example, right? But no need to change the cavity in order to change the resonant frequency. I want to save you time on this, okay? So why care about cross-Kerr? Here I want to give you some calculation. If my readout pulse is 200 nanoseconds, and then what is the spectrum width? 1 divided by 200 nanoseconds is about 5 micro, right? So what I'm saying is this. This is the pulse. This is 200 nanoseconds. Then in the frequency domain, right? This is F. This is T. The half width full maximum, right, is about 5 megahertz. Right? Or what? I don't know, maybe 10 megahertz. I forgot the equation. But of course, narrower, longer train, narrower pulse, right? So you will need a cross-Kerr about 10 megahertz to be safe. Because you want to distinguish them, right? If yours is too close to each other, how can I distinguish this pulse, right? Because if this is 5 megahertz, and then you only have, let's say, 2 megahertz separation, it's difficult to distinguish because you still have noise to consider. Okay, so that is one reason, one way to calculate. So now,
As you actually working closer together, then isn't it easier to just like you're looking at the real parts? Isn't that separation is going to increase between them as they get closer together?
Yeah, for this part, right? But then you also have the imaginary part to consider, because now you actually need to rotate it to the... Actually, what I'm showing you is an extreme case that you only have real part different. But what we're plotting here is the imaginary and real part, and then we rotate it to the same here. Yeah, so yes, looks like the case, but if we really do the math, I believe it is not the case. And we also have the math, the noise. Yeah, good question, right? Yeah, and you also don't want to operate in a region that you have such a steep slope. You will run into other problems. Then how about the accuracy? Yeah.
In terms of like the Cross-Kerr, when we're trying to calculate it, does the simulation give it to us, or do we have to calculate it like this?
The simulate, okay, I'm going to show you actually. So let me let me go through step by step. Now I'll just take this opportunity to learn what accuracy you need to set up. For example, in this example, if the Cross-Kerr is 10 megahertz, and my mode is 6 gigahertz, then it means you have about 0.17 shift in the frequency, right? Percent. Then your convergence criteria should be smaller than that. Because convergence is say that if you don't change any more by that much percentage, then I assume it converge, right? I'm telling you to use 1%. It's way larger than this. But because that's a class project and also it's not well designed due to my problem, so that's why I don't want you to go to so deep. I just want you to appreciate what it is and accept that the mesh is good enough or whatever is good enough. Yeah.
I think this is setting the frequency simulation bit, right? Frequency.
No, frequency at the convergence. Actually, it's not shown here. So there is a convergence setup that you say until what percentage you assume it is converged. So when you do the simulation, for example, this is the frequency, this is the Q. Let's use the Eigenmode, right? This is the omega 0, right? So you usually will see something like this, right? Not F, number of paths, right? Number of paths, right? By the way, what does HFSS does? It starts with a coarse mesh. It simulates. You get this data. And then you refine it and simulate. And then you find that, wow, that is a big change. Maybe 20%. Then you say, no, I'm not at the solution yet. Then you keep refining. And then eventually I find that, wow, this is less than 0.1%. Then I stop. Otherwise, how does it know what is the correct solution, right? So then you stop here. So what I'm telling you that if you are doing real research, you need to consider this for the convergence. But for this class project, 1% is good enough. And also, I said that limit it to 10 passes. So it's possible you even cannot limit 1%, but when you reach 10 passes, you say, I'm stopping here. Okay, just take that as a result. So I give you some leeway. You even can claim that if you cannot explain something, you can say, because it doesn't converge and it does not allow me to do better convergence. In terms of convergence, also in the future, you do research, it is often just converge on real frequency only. That will help you. Otherwise, it is difficult to converge.
So we want that.
Oh, you want to click it. Yeah, converge on real frequency. Now, this is an example. There's a Josephson junction here. Again, I cannot model Josephson junction, right? I only put this inductor here, right? And sometimes you need very dense mesh. So in the project I was doing, I need to go to very small mesh and very dense because this is a very tiny stuff. And the energy concentrates there. You can try to plot the E field. You see a huge E field right at that region because the L is very large. Now, then you ask me, where do you get the results? It will all outputs to your Qiskit metal, right? You call HFSS, and then HFSS take all the E field distribution and then do the calculation I just mentioned to get the energy participation ratio. Here, only 2 mole, right? 0 mole, how to say? Yeah. And then it diagonalize it. This is the Cross-Kerr. Okay? And it has 2 things. I forgot which one. I think this is the analytical one, this is the numerical one. Sometimes you get different results, pretty different results. So you can capture both. Because I'm not asking you to achieve a certain target, right? I just want you to tell me how it changed when you change your design. Okay? And here also give you the Q is another place. This is the eigenfrequency, but you should be able to read it. Is that okay? Yeah, so I see it's 5:45 already. I have not finished this qubit, but next class I can finish it maybe in half hours. And then we will go to new topic. I want to talk about some microwave stuff. And then we go to trap ions and others. Okay. Looks like I'm about two classes behind the original schedule, but I think it's necessary. Right? So, okay. Let's stop here. Yeah.
The preferred tool for modeling those things. So